Welcome to the second part of introduction of filters. In part one, as part of the introduction of filters, we looked at a terminology called impedance, which we all know well. So we defined impedance as a resistance to current flow. And we also saw how to combine different impedances in our electronic circuits. We have most common circuit elements: a resistor, a capacitor, and an inductor. And we've also seen how these three components have resistance to current flow. In the case of a resistor, the impedance that was R, and in the case of capacitor, the impedance of a capacitor is 1 over j omega c, and in the case of an inductor, j omega l. Okay, in our discussion in part one combination of these impedances resulted in a unique type of filter called low-pass filter, and we have seen how it was possible to pass low-frequency signals while damping high-frequency signals. In this lesson, we will see some more of these impedance combinations and the filter types they will result in. Now, before that, to strengthen our imagination of how these impedances shape the output of a circuit, let's see what their property signifies in a circuit. So if you have frequency versus the gain, which was V output over V input. Now, when you have only a resistor in your circuit, the impedance is not dependent on frequency, so the value of the output over the input will be the same throughout, regardless of what frequency we're working with. So that's the case of a resistor R. In the case of capacitor, for low frequency values, we'll have high impedance, and for high frequency values, the impedance approaches to zero. So for low frequency values, we'll have high impedance, and our capacitor acts as if it was an open circuit. And for high frequency, the impedance decreases, and our capacitor acts as if it was a short circuit. Now, in the case of an inductor, then we see that it is linearly dependent. So increase in frequency results in increase in the impedance, and decrease in frequency will result in decrease in the impedance value. So we'll have a linear relationship between frequency and the gain. So we'll see how this property plays an important role in visualizing what type of filter we will have based on the combination of different type of impedances. Let's look at the following circuit. So we have a resistor R and an inductor L. Now our intention is to find out what the output voltage across the inductor is. That's V out for an input voltage Vi. Now we know that the circuit elements we have here are a resistor with an impedance of R, and an inductor with an impedance of j omega L. So based on the discussion from topic 1, we can calculate the voltage across the inductor based on voltage divider rule. So V out will be V in times impedance at the inductor over the total impedance. So that will be the inductor impedance is j omega L over the total is R plus j omega L. R plus j omega L. Okay. Once we know this, we will be interested now in this part of the solution, which either amplifies or attenuates our input to give us our output. So what we can do is, therefore, we're interested in the ratio output over input Vi. So this is j omega L over R plus j omega L. Okay, so as always, we'll consider the following cases. Case 1, we'll look at the case where our frequency is too low. Okay, we're looking at what the output voltage across this inductor is at low frequency. Now this is easy when you study this graph here. For our inductor L, we can see that at low frequency we have short circuit. So at low frequency is short circuit, so therefore if that's short circuited, then the voltage output across this will be very low. So V0 over Vi will almost be 0. Okay. And so it will take the inductor response property, which is a linear curve for low frequencies. Now in case 2, we look at where our frequency is higher. Okay, so at high frequencies, our inductor is acting as an open circuit, so the voltage across is almost similar to the voltage input. Yeah. So V out over Vin is almost 1. Okay, this will tell you that Vi equals V out. Okay, our response graph, our board graph will look like this. So at low frequencies we have something like this, and at high frequency we have gain which will be 1. Okay, so what we would expect is as frequency increases, then the graph will continue. So this is again a special type of filter called high pass filter, or HPF. This filter attenuates low frequency signals and only passes high frequency signals. Let's look at the following circuit. We are interested in the voltage output, okay, across the resistor. And we know that we have 2 circuit elements, and their impedances can be given by, we have a capacitor and its impedance is 1 over j omega c. Okay, and we have resistor whose impedance is just R. And the output voltage can be given by the voltage divider rule that we have seen in part 1 of the filters introduction. So that will be the input voltage multiplied by the impedance of the resistor over the total impedance, which is R over R plus 1 over j omega c. Okay, so this can be simplified as follows: V in R times j omega CR over 1 plus j omega CR. Okay, so we are interested in the ratio of this and see how V out. We are interested in the ratio of the voltage out to the inputs. Okay, that will be j omega CR over 1 plus j omega CR. Okay, we will look at some cases to actually simplify for us what the response of this circuit looks like when omega changes. Okay, so case 1, what happens at low frequency? Okay, at low frequency we know that the capacitor acts as an open circuit, so much of the voltage will be dissipated across the capacitor and the voltage output is almost 0. So V out over V in almost is 0. Okay. And case 2. Now what happens when omega is very high? For high frequency, then we'll see that adding 1 to already a very high number is meaningless. So this V out over V in almost equals j omega CR over j omega CR. You could also look out for higher frequency. You see that the capacitor is acting as short circuit. Okay, therefore voltage output is almost similar to voltage input. Okay, then we can graph this omega, and we have V out over V in. Okay, we're interested in the magnitude. All right, so for low frequency it's almost 0. Yeah. And for high frequencies we have the ratio will be 1. Okay, so high frequency 1. Connect this like this. So as frequency increases, that's how the curve unfolds. So this is also one type of high pass filter. You can see that low frequencies are being attenuated, but it's passing high frequency signals.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.